So you want to stop it really fast and then... Okay, so we're spinning eggs to see which one is going to keep spinning after we stop it, because that one, with inertia from the contents, is not cooked.
I said this is cooked.
Okay. And you guys are spinning.
The problem is that it's kind of...
So when you stopped it, it just kept right on spinning like you hadn't even stopped it. So you think that one's got something inside that has inertia and is moving.
Here, can you hear it?
No, but... That's cheating. Okay, so everyone took their votes. Hard-boiled, raw. Max is going to spin. I'm like doing the no-no of filming and doing it sideways here.
That's just I had different observations. It's like every experiment, like observe.
You have to stop it fast, like.
For the win.
That one kind of keeps going.
Oh, there's fireworks now.
Watch flower. Wear safety glasses.
Oh, definitely this one's.
Yeah, see how... Here, try this one.
That is so cool.
I guess we'll have to crack them open. See if we're right.
Yep.
Okay,
This one's so cool.
Definitely wrong.
I can view this one.
Look at this.
Yeah.
So,
That's so weird. Stop it and it just keeps going. Look at her.
so you guys told me you think these two are cooked.
Look, look.
Yes.
This one's raw. That one's hard boiled.
This one's definitely, you're right.
I think this one.
I think this one's cooked.
This
We're gonna have
one's...
to test this one. Let's test
All right,
this one.
you got them right, guys. Good job.
We cracked this.
Yes.
No. I'll put the two. So, I cracked the two hard-boiled ones and you were right. No need to test these. I know two weren't cooked.
Nice, we were right.
So, good job. It is confusing, though, to think and to, like, learn how to stop them.
Also, the colorization was a little bit strange.
Yes, I didn't
And the
think
weight.
that through.
And the weight,
Mm-hmm.
like, even if you were blind or whatever, like, you could probably
Feel the difference. Yeah. Yeah. So, I need to find my marble, which involves dumping out everything from my bag for the 4th time today. Okay. And I don't know if I can do this with a block of wood. My beaker is missing. Yes. Can you eat the eggs?
That is gross.
No. They've been at room temperature for quite a while, so probably not a great plan.
They smell so bad.
Let's see. I am not sure. I'm going to use, I think I'm going to use the egg. There's some friction. Okay, so another sign of inertia. Half my stuff is in the nursery because I had to wash a ton of dishes after chemistry. But this is too big. Does anyone have a penny or a dime or something? I'm broke. Give it back and everything. This is not one of those magicians that steals your money and throws it up. Penny, dime, anything, little coin.
I have like a little piece of shell size of it.
We'll go for that if nobody has any coins.
Oh, I want a nickel.
I don't carry them anymore. I used to carry them.
Get the biggest piece of shell. The shell is so round, so.
Say hello, guys. It's like, look away, Dixieland.
Let's see if this works. Ooh, this will work.
Somebody's little star here. Okay, so here's the thing. Everything has inertia. This will resist changing its state of motion. If it's sitting here at rest, it will resist changing that. It wants to stay at rest, and unless it's acted upon by a force. If the force isn't great enough to overcome its inertia, it will continue to stay at rest. So the idea here is, if I used a glass, it would be a lot easier, but my glass is in the nursery. If I flick the part out from under it, the inertia of the little metal thing should remain constant, keep it from moving, and it should just drop straight down instead of going with the card. Yeah, no, not that.
It's also tilted. The surface underneath the card is not. What if?
Yeah. What if it doesn't work? haha, it worked. The little guy fell in the cup because the force of friction between the card and the little metal thing wasn't enough to get the little metal thing moving. So it just remained where it was, and when nothing supported it, it just fell down because of gravity. And it did it again, see? And it's more obvious with a cup because you can see. But all my cups are full of caustic chemicals at the moment. So it makes it a challenge. So Newton's first law, who'd like to tell me in their own words? Actually, I'll from you guys because that's much more interesting than watching me. So who'd like to tell me about Newton's first law again? Next.
When an object is in motion or at rest, it tends to stay in motion or at rest until acted upon by an outside force.
Right. And the force has to be big enough to get it going. And we'll learn more about what that means later when we talk more about friction and air resistance. But yep, Newton's first law, perfectly. Did you all read about Newton's second law this week? Not yet. Okay. So Newton's second law gives us a powerful mathematic tool. I don't know. Will that work? Maybe, kind of. And the tool that we get, no eraser in the tool that we get from Newton's second law is this equation. Is it on? I never ever say Newton's second law like with the kind of word definition. For Newton's second law, I just say F equals ma. If the test asks you for Newton's second law, you write F equals ma, that's great. That's all you need to have for that. And what that stands for is force is equal to mass times acceleration.
So that's Newton's second law.
Newton's second law, F equals ma. So if I know the mass of this brick, and I know the magnitude of the force I apply to the brick, then I can calculate the brick's acceleration. If I know the brick's acceleration, like if I have a little speed gun or acceleration gun, like if you go to physics day at Six Flags, they can strap accelerometer machines to you on a roller coaster, and you can plot the acceleration at different points on the ride. So if I can measure the mass and chart the acceleration, I can see what force the thing is experiencing. And physics day at Six Flags, you also can carry a force meter on rides and see what kind of forces you're experiencing on certain rides. But it's a powerful tool to help us. If we know two of these things, we can figure out the third of them. All right. Okay, so we've got two of Newton's laws today, and they have shocking ramifications for our life and how people thought about motion, because people thought matter has a preferred state. It wants to be at rest. It always goes back to rest even when it's moving, but that's because people didn't understand that there was friction before Newton put forth these ideas. Let's go over the summary, the study guide. Let's go over the study guide, and then we'll start talking about some of the math for next week. Okay. No, one word. I changed my mind. Okay, Newton's third law while we're at it. What's Newton's third law? Does anyone know off the top of your head? Chris?
I just knew it. It was,
Where reaction is equal to opposite reaction?
Yes, and that's exactly what the folks said. I always say, this is physics, we don't worry about actions, we can't quantify actions, so for every force, there is an equal and opposite force. Okay, so Newton's third law is misunderstood sometimes. And this is why. Okay, so let's say I'm applying a force straight parallel to the ground to this chair. Okay? Newton's third law says there must be an equal and opposite force. What is it? Joseph?
The chair's pushing back on the plate.
Okay, so I'm pushing on the chair, and the chair's pushing back on me. Okay, so the force, me pushing on the chair, and the equal and opposite force, the chair pushing on me, are, just reversed. I push on chair pushes on me. Both forces aren't applied to the same object. It's not like I push on chair pushes on chair. And so when people say, well, you can't move anything according to Newton's third law because, you push on chair, there's an equal and opposite force that keeps the chair in place. Well, both the force and the equal and opposite force aren't applied both to the chair. One's applied to the chair, one's applied to the thing pushing on the chair. So, I push chair pushes me. Yes. So, like brick, right? I push brick. What's the equal and opposite force?
Brick is pushing me.
Brick pushes me, right? I jump on earth. What's the equal and opposite force?
Earth jumps on you.
So I push down on the earth pushes back up on me. This is obvious because I didn't just fall through the floor. And thankful. Right.
You didn't go to the ceiling. The earth didn't jump on you.
Yes, didn't jump on me. I push down on the earth pushes back on me. So the force and the equal and opposite force are applied to, not the same object, but the opposite object, basically. If that makes sense. So when we apply the concepts of these, so I've got a little plate. It's a sad, tiny little plate. And hopefully, well, maybe I'll leave it intact for a second. So, if I hadn't cut that plate and it was all smooth, and I hope the marble will go around the plate. I can get the marble just flying off the side. If I get the marble going, the marble, of course, goes in a circle, right? So what if I cut the plate so the marble starts going around in the circle, and then eventually, what will happen?
The marble will go out of the plate.
Okay, so will the marble go out of the plate like that?
No.
Like that? Or like that?
This goes out.
Okay, so which of Newton's laws, if I can get it to go around the tiny plate, which of Newton's laws would describe the fact that the marble goes straight instead of continuing on its path that it was on? Why?
Because
It's cut off.
it wants to stay in motion unless I can combine outside force, and after the plate swallows and pushing on it to make it go in a circle anymore, it just keeps going straight.
Okay, so you said the marble wants to stay in motion because it is in motion. So what force is acting on it to make it go in a circle instead of in a straight line? I'm actually going to put here, the marble wants to go in straight line motion because that's what everything wants to do. Plate. Okay, so then what do we see when the edge of the plate's Joseph?
And it just keeps going in the direction of left.
I guess I'm standing on the plate. The marble continued in the straight line. Now, if the marble had not been rolling on the table, if it had not encountered air resistance or friction with the table, what would have happened to it?
Kept on going.
Forever and ever. Yeah. And you can see, of course, how hard it was for people to actually believe that was true, but there he is. So now let's look at the study guide. I think the test has all 3 of the definitions on it this week. Next week. I mean, don't take a test this week. You have one more week of this module course. So let's start with study guide number 2, and we'll start with Lily. It
You have the same
says-
questions?
Oh,
Or is yours old?
I think mine's the same now, but I could be wrong. Let's actually skip number 2 because we have all 3 of them written right there on the board and just talk about that. Make sure you know all 3. The test, I think, actually
doing
does
a
ask
study guide?
all 3. Study guide for module 10. The second question says state your 3 laws. They're up there. So we don't need to do that. So Lily, how many of these did you all do this week? 6, okay. In space, there's almost no air, so there's virtually no friction. If an astronaut throws a ball with an initial velocity of 3.0 meters per second to the west, although how do you figure out what west is in space? I don't know. What will the ball's velocity be in a year?
It will be 3 meters per second to the west because there's no friction stopping it. It's just going to be going the same speed.
Right. And which of Newton's laws tells you that?
The first one.
Yep. It's not being acted upon by an outside force, so it will just continue in the same kind of motion it's going in indefinitely. So Jenna, a boy is running north with a beanbag in his hand. He passes a tree, and at the moment he's beside the tree, he drops the beanbag. Will the beanbag fall next to the tree, or what might it do?
I said it would be north of the tree.
And how do you know?
Isn't it because, like, when he drops it, it would, like, leave his hands, like,
Doesn't it have the same velocity as the
Speed
boy?
difference.
So if I drop something, not that I can do a whole lot of running, and today especially, but if I'm running and I drop this thing, it had the velocity that I have in this direction, so it will just keep soaring along next to me and hit the ground right next to me, assuming I don't change velocity as it's falling. It won't just fall straight down while I continue on ahead. It's going the velocity I'm going, so it will just fly along parallel to me until it hits the ground. And you can try that out. I make them do it in physics. If they don't believe me, they have to run and drop stuffed animals.
I don't think.
Think you want to run?
Nah, I guess so.
You're good. Here, take the brick and start here, and you can run that way. And he just needs to get his energy out. Oh, there's a note for me on that one. Put back according to the picture.
Okay.
So if you hold that out, you get up some speed, and then when you get, within a few feet of the wall, you can drop it so it has time to actually fall. See, it stayed right with him. It didn't fall behind where he was. He probably slowed down though, because running headlong into the wall is a bad plan. Thank you. Let's see. So we're on Ava, Elise. Suppose a situation in question 4 is changed. The boy runs, and when he passes his friend next to the tree, the friend drops the beanbag. The friend's not running. What will happen? Right. And why? Right. So if I'm just standing here and the guy runs past me and I drop it,
You don't have any velocity.
right, it has my velocity, which is not moving, not his velocity, which is something north. So obviously, it's not going to just like
Start moving with
magnetize
him.
onto him and start flying in that direction when I drop it